So today we're going to continue with functions, but I do want to draw your attention to the fact that we posted on Piazza about next week, which is the Fix-It week and exam week. That has all the details that you need to take care of everything during the next week. In particular, again, you can resubmit one lab, one hack. They are all now open except for 3 and 4. 3 will be open later today after we've graded everything, and 4 will be open later because, of course, it's not due yet. The way that it's going to work is if you want it reconsidered, submit it now, and then go to your lab section, go to your hack session, and talk with an LA. They'll regrade it right there in front of you. They will enter in a new grade into Canvas. They'll also be taking the data so that we've got it somewhere else as well, so that you can't just go to another section and get another hack done or something like that. Yeah. You go to your lab and you get your stuff checked off. There's nothing new due next week except for the exam. So if you have nothing, as it says, if you have nothing to return in or reconsider, you don't have to go unless you want some extra help or something like that. It is all to prepare you for the exam next week. The exam is on Friday, September 23rd, which is 1 week exactly from today. There will be no lecture that day, so I won't be here. Instead, the instructions will open automatically on Canvas at 9 a.m. Right? You'll have 2 programming exercises, each worth 25 points, with the exact same distribution as a hack. It was graded on style, documentation, design, and heavily based on correctness. Right? It is open book, open note, required computer in that you have to have a computer to write a program. We're not going to have you write a program on a blue sheet that's not 1980 anymore, whenever they did that. Right? Instead, you can use your own personal computer. You can go down to the lab and use that computer. You can use whatever computer you want. You may resubmit any number of times. Those 2 exercises are designed to be done in an hour at most, and we're giving you a 15-hour window. Right? You can start anytime. You can then go to lunch. You can come back and do it and resubmit if you want to. The time is yours. It is extremely flexible. So with great power and great flexibility comes great responsibility. What you cannot do is consult with anybody inside the class, outside the class, or anybody, period, right? Your hacks and your labs are highly collaborative. We want you to do that. But your exam is to show that you are actually picking up the material. So do not discuss it with anybody. Do not share it with your hack partner. Do not share code with anybody. Do not receive code from anybody. You can discuss it all you want after midnight. It is due on 1 minute before midnight on Friday, September 23rd. After that time, you can talk about it all you want. A 15-hour window is more than enough to deal with any personal issues that come up, any technical issues, any issues that come up at all. I mean, you've got 15 hours. Right? As long as you're not starting at 11:30, right, then you should be okay on this. Right? If you want to take the lecture time and do it during then, and then extend that lecture time or whatever, go ahead. Right? If you want to bring your computer and do it in here, and it might be quiet, I don't know. I don't know how many people will show up or not. But otherwise, you can take it in any location you wish. Okay. This is a highly flexible, asynchronous, executable exam. Not many people do it like this. And we have had mostly success doing it this way over the last 3-4 years, but there have been some failures. Those failures have been individuals who have posted the exam to a cheating website, and guess what? Guess what? You're not the only ones who know about the cheating websites. All right, everybody knows about them. We can Google too, and we can find them. And if you are sharing it widely like that, guess what? There is the probability that somebody else is going to take that answer for their own is very, very high, right? That's how we catch them all, right? Because we use this program called MOS, Measure of Software Similarity, which actually has existed far longer than any other plagiarism detection software. When you write your 5-paragraph essay and you turn it into Canvas, it gets run through Turnitin, which is a plagiarism detection software for essays, right? Software is far more structured, and it is far easier to detect those kind of things with software than it is even just plain English. Moss dates at least 10 years before I ever saw any plagiarism detection software used in some other discipline. Why? Because we're all computer scientists and we know what we're doing, right? We know exactly how code gets copied. Somebody asked if there is any false positives in the morning class, and I said, not really, because what is a false positive? A false positive is when it gets past the plagiarism detection software because somebody rewrote it to the extent that it was no longer detectable. And I pointed out to them, what did you just do, right? You took somebody else's code, you rewrote it so much that it was so different that it was no longer the same, and it solved the same problem. You wrote the program, right? Congratulations, right? In fact, you wrote the program with extra steps because if you'd just written the program from scratch, right, you wouldn't have had to read and understand somebody else's code, which, by the way, requires a far more higher cognitive skill than just simply writing the code. Right? So no, there are no false positives. Of course, when we run this, we do, of course, then look at it manually and say, well, yeah, that's obvious. Usually when somebody copies, they don't even... Last spring, somebody copied and they didn't even bother changing the name. So that's that ridiculously easy. Right? So my message to you is I'm not going to be a cop. I don't want to be a cop. I don't want to adjudicate this garbage. Just don't do it, right? Please. You will be caught. And by the way, if you've gone through CS10, you might know that the School of Computing has a 3 strikes and you're out policy. 3 strikes of plagiarism in a course or multiple courses means that you're out of all the programs. Right? So keep that in mind. Right? Any questions on the exam next week at all? No? All right. All right, so to continue on functions, remember that function, and again, we're not expecting you to use functions or on your hack this week or next week. It's perfectly fine if you do. Great, do it, but do it correctly and make sure that it actually runs in the grader. All right? If you want, what I'm going to show you today is modular programming where you take the functions that you've written and separate them out into other files. That is not specified in the hack, and it will not be specified in the exam, so don't do that part. Right? But if you want to write your own functions like we did on Wednesday and have a get monthly payment, round to cents, whatever you want, you can put that in your hacks. Okay? But a function is something that takes input and produces at most one output. You can have a void function that produces no outputs. We use functions because they provide reusable pieces of code. They provide a procedural abstraction where we don't have to worry about how the function works. Instead, we just have to use it to solve the actual problem that we're trying to solve. As with functions, or as with variables, you have to declare your functions, and in C, that means creating a prototype. The prototype is the function name, its inputs, delimited by a comma, and a semicolon right here. And then, of course, the return type. What type of variable does this function return? You should always have doc-style comments attached to the prototypes so that you explain what the function does. Then down below, you can go ahead and provide the definitions. But now, think about this. If you've got, say, 10 functions, maybe that's not so bad. What if you've got 20 functions, 30 functions, 100 functions at this point because your system is so complex, right? Are you going to put those all in one big giant file? No. You want to organize your code. C didn't do that. They took stuff that was standard in the standard library and put it into the standard library. They took input-output stuff, printf, scanf, and put it into this stdio library. They took math stuff and put it into the math library. And now we're going to take our stuff and put it into our library. Right? And that's what modular programming is about. It's organizing code into different files. Right? Not all functions should be in the same source file. Right? This is bad organization. bad design. Instead, they are separated into different files. Can't spell today. Can't type, I guess. I know how to spell it. The header, or the prototype and documentation goes into a header file with a .h extension. Where have we seen that before? Math.h, stdio.h. Now we're going to do the same thing. We're going to put our stuff into myawesomelibrary.h, whatever that happens to be. Right? Then you take the definition, implementation, goes into a source file with a .c extension. There we go. With the same name, with the same base name. So in other words, if you named it myawesomelibrary.h, then the source file should be myawesomelibrary.c. Okay? Let's do that with our lone program over here. Right? So I'm going to go ahead and create a couple of files here, but you're going to help me with the naming. Right? So what do these two things do? Get monthly payment and round to cents. They do math stuff. Should I put it in the math.h library? No, that's already taken. Besides, it's not general math. It's what? Financial stuff. So finance.h. What's the difference between finance and financial? Any business folks to tell me? All right, I don't know either. Let's go with finance. All right, fine. And then finance.c. Same base name, finance and finance, but .h and .c. And what I'm going to do, I don't need the demo anymore. What I'm going to do is I'm going to take the prototypes and their documentation, and I'm going to move them over to the header file. I'm going to take the implementations, the definitions, and I'm going to move them over to the C file, the source file here. All right? Take a look at that lone file now, right? Now, take out all the comments that are directives to, as part of a demonstration here, and much smaller, right? Only 60 lines of code, right? Probably only 40 lines of code after it's all said and done. Right? Much better organization, right? Except that the problem now is, can I compile this like I was before? Let's try. GCC, what was the loan? Yep, there we go. Uh-oh. What's it telling me? Warning, I don't know anything about get monthly payment. We use that up here on line 33, but do you see it anywhere declared? No, because we took out our prototypes. Do you see it anywhere defined? No, because we took out our definitions, our implementations. So what do we need to do? We need to do exactly what we've been doing up to this point. Bring that library in so that you can use it, right? You want to use the square root function, you include the math library. You want to use the get monthly payment function, you include the finance library that we just made. But you do it a bit differently. You use double quotes instead of Langle-Wrangle, right? Now, you could use Langle-Wrangle, but that's bad style. And I'm just going to have a slight digression here. Basically, what happens when you use the Langle-Wrangle? It tells the compiler, hey, this is probably a standard library. Go out into the standard spot and look for it for me, please. Right? And it goes there and says, okay, well, I see the math library. There it is. Right? After you told me -lm to link into it. I found the stdio library. Great. Right? If it doesn't find it, if I did this instead, Langle-Wrangle on my finance.h, what it says is, I'm going to go ahead and look for this in the standard spot along with all those other standard libraries. And if I find it, great. It ain't going to find it. Why? Because it's my library. It's a user-defined library. So what it's going to do is it's going to say, okay, I'll start looking in other places. I'll look in the current working directory, and indeed it's right there, and it's successful. Right? But by doing double quotes, it's telling the GCC compiler, don't bother looking in the standard location and waste your time. Start immediately right here. And that's better style. Right? Yeah? Yeah, there's precedence, so it would grab that one. Don't worry, there's not. I'd be very surprised if there were. Right? So you do have to be careful, because if you want to bring in two libraries with the same name, you have the same problem as with two functions with the same name. Right? Now they're conflicting names. Awesome library and awesome library. Right? Now you have to be a little bit careful about how you do that. And that's going to require include guards and conditional compilation and a bunch of other stuff that we're not going to get into. Way too complex. All right, now that I've included the header, it should work, right? Except it doesn't. That's the exact same error message that you get when you do not use the -lm flag. If you use sqrt and you don't use the -lm flag, it gives you this message. I'm trying to compile into an a.out file, but I have no idea where that stuff is. So to solve that with the square root function, you provided -lm. We're going to do the same thing, but for our library. Right? Let's take a look at finance first of all and fix some things. When I have function definitions here, what do I need? Have I declared them yet? Nope. I don't see any prototypes here. How do I bring those prototypes in? How did I bring those prototypes in over here? By including the header file. We do the same thing over here. Do I need to bring in anything else? I see POW. I see round descents. Well, I know about that one because I brought in this header file here. Is that it? That looks like, oh, and I see round. Round and POW. Where do those live? In the math library. It's also best to also include the standard library, no matter what. It'll be provided for you, but do it explicitly. And then math.h. Now I've included everything. Do you see a main here? No, I don't see a main. If I tried to compile this normally, finance.c, right, it's going to complain that there's no main. Right? And of course, it's also going to complain that I'm not linking in the math library, so let me get rid of that. Right? There we go. And undefined reference to main. I can't build an a.out file. This is just a library. You can't run the math library, right? That doesn't make any sense. It's just a collection of functions. This is just a collection of functions. Right? We're not going to run it, so we're not going to compile this into an a.out file. Instead, what we're going to do is compile this into an object file. So what flag did I just use there? -c, -c. Do we remember that from the first week? I gave a really quick demonstration of how code starts from C. It gets compiled to assembly. That assembly then gets compiled into machine code, and now you've got machine code, right? A bunch of zeros and ones, right? The thing that I used to do that was -c. Compile this library, but do not produce an executable file. When I do that, it produces, let me go ahead and refresh this, a finance.o file. If you remember back in the first week, we produced a hello.o file, right? And this is a finance.o file. Somewhere on the system, there is sitting somewhere a math.o file. Somewhere on the system, there is sitting an stdlib.o file, right? Compiled code for that system. Let's try to open it up. Failed. Why? Binary. Let's take this leap together. Open it anyway. Okay, no, it's not going to let me. Right. I can try to more it. Finance.o. And it's going to tell me it's not a text file. If I put this out as text, it would just be a bunch of garbage. But I also showed you Hex Dump, that you can actually take a look at the internals of this file. What is it? Numbers. Binary. Right? Hexadecimal, base 16 instead of binary. Right? But it's still a binary file. Right? Okay, so how do we use that? Now I need to link into it. Normally I would use -lm to link into the math library, but because the finance.o file is right here in the same directory, I just use it. gcc, loan.c, finance.o, and of course I need to bring in the math library. Okay. When I do that, it produces an a.out file that I can use then to do my loan amortization table. $10,000 at 5% interest over 5 years produces the same output. All right? So what was that process? Here's the demonstration. Right. So one, we separated our files, of course. We included the header file using include finance or finance.h, right? Yep, finance.h. All right. Anywhere we needed to in the loan.c and finance.c files. All right. We included other headers as needed, right? Say math.h, right? We then compiled, right? We compiled the finance library using the -c flag. So gcc -c finance.c, right? Which produced an object file containing the actual machine code of our library. Then we compiled everything together, using gcc loan.c finance.o and of course finance.o and of course the -lm flag in order to bring in the math library. So if you brought in another library that was installed in the system, you'd have something like -l and then the name of that library. You can configure GCC to do a lot of things. Well, that's not installed there. I installed it over here because I'm not a sys administrator and I don't have access to install it system-wide. So I installed it over there. Look over there instead, right? And all of that is arcane GCC knowledge that I have. Whenever I have to do it, I have to look it up because I don't remember that stuff, and you shouldn't have to remember that stuff either. And then I have to write it out and and come up with these massive rules for building all of your code, right? Hopefully there's something to help me with that. And there is, right? We'll talk about that in a second here. But otherwise, what else would I want to say? Oh, yeah, pitfalls. You never, never, never include a source file. Right? Include, say, finance.c. There we go. With a hash, sorry. Why not? Let's look at what happens when we do. You only ever include header files, right? And we see this over and over again, and that's why I'm emphasizing it this semester. Never, 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 never do this, right? And anytime when next time somebody asks a question and I look at their code on Piazza that they included a source file like this, I'm going to time index this video and simply post that, all right? Never do this. Why? Finance.c. I'll go ahead and try to compile this. And then we'll talk about how this is actually working. I put the compiler into an infinite loop. Hopefully, eventually it's going to die. Right? But we'll wait for it, right? We'll wait for it and until it does die, and then we'll discuss why this is happening right now. When you include a header file, right? Well, let's go back to something else that we've seen. Finally, it died. Right, there we go. When you say define, I don't know, miles per hour to be 60 miles per hour, right? Remember we did this in the first couple of modules to get a constant, and I described how this worked. The preprocessor, before it even compiles, goes through your code, finds any instance of MPH, and then does a cut and paste replacement with 60.0. Right? The preprocessor does that. How do you think these includes work? They're exactly the same. All the preprocessor does is says, I'm going to go out to that file, cut and paste. Right? Cut and paste, cut and paste. That's all it's doing. Now what happens when I screw up? Let's get rid of this. What am I cut and pasting now? Myself. Myself being the finance.c file. So let's do that. I just cut and pasted, and I've got two definitions of everything. Except that, what else do I have? Another include. Cut and paste myself. Cut and paste myself. Cut and paste myself. Do you see why the compiler screwed up? Right? Don't do that. Right? Always and only ever include header files. Okay? Otherwise, you'll send this into an infinite loop, or at best, it just won't work, right? Okay? So pitfall, you never, never, never include a source file. Only include header files. There we go. Otherwise, infinite recursion. Advanced solution? I don't even want to call it an advanced solution. If you have many source files and a more complex system, more complex program, right, it can get very unwieldy, very inconvenient to have to recompile every single time. Instead, what I want to do is I want to have one command that compiles automatically for me. That'd be great, right? Do it, please. That's what we want in all of our programs. Just do it for me, please. Do it for me, right? And fortunately, there is a command, right? It's called a build system. Most languages have some sort of build system, right? A second system that manages that. Here, I'll enumerate them. Manages dependencies. So what is a dependency here? In order to compile the loan program, what am I dependent on? Well, I'm dependent on the standard libraries, but those are going to be there no matter what. I'm also dependent on the finance library that I just made. So what has to happen before I compile this loan program? I have to compile the finance program. What if the finance program or the finance library relied on another library? Right? Then you'd have to compile that one first. A depends on B, B depends on C. You have to go in that order. C, then B, then you can do A. Right? That's a whole chain of dependencies. And maybe you don't have that library. Maybe you need to download and install that library, right? Or a bunch of other rules that come into play, right? Manage dependencies, track changes so that only changed files get recompiled. There are systems that are large enough that you measure compile time on the order of hours, right? I'm not sure about it, but has anybody ever compiled from scratch a Linux system and installed it? Certainly an installation of a Linux operating system, that only takes maybe 10, 15 minutes, right? Anybody done it? All right, how many minutes did it take? 15 minutes, right? Imagine if you compiled that from scratch. Right? It compiled the entire Linux kernel from scratch. That's going to be maybe, I don't know, maybe you could get it down to an hour or so, but it's going to take hours, right? Because of a whole process of bootstrapping and bootstrapping. Now, if you've got this system that takes hours to build and you change one thing, all right, I'm going to lunch. I've got to recompile, right? That's always the programmer joke, right? Well, you took a 3-hour lunch. What's wrong? Oh, I'm compiling, right? You always tell the manager that, right? I can't do anything until it's done compiling and testing, right? And then managers that don't know any better, they'll fall for it, right? But anyway, if you only have one small change, you shouldn't have to monolithically recompile everything. You should only be able to have to recompile the one thing that was changed and anything dependent on it, right? And a build system does that for you. It manages dependencies, it tracks changes, it provides multiple ways of compiling for different systems, etc. It provides a whole bunch of features. You do not have to learn and use a build system here. Anytime that we give you code complex enough that needs a build system, we give it to you. For example, not next week, because of course it's Fix-It week, but the week after that, we give you a lab that involves an image manipulation program. Let me jump ahead here to Lab 5 in week 6. Now, by no means is that a large project, but there are at least a half a dozen source files, right, that have to be compiled in a certain order and in a certain way. If we gave you those instructions, they're going to be error prone, right? You're going to mash the keyboard and get one thing wrong and have to start over, right? So instead, what we've done is we've given you what's called a make file that specifies how this project is made. And it's a whole nother language, right? It's a language with variables, and it's a language with rules. So these are my variables up here. CC, that's my compiler. Right? And my compiler in this case was GCC with a flag of use the GNU 99 standard. Right? We've got other flags here. The wall flag, that should be familiar to you, right? You should always be running that. Includes, I want to link in the math library. Right? Those are my variables so that I don't have to reuse, I can reuse those variables, and anytime I want to change it, for example, if I want to change GCC to a different compiler, say Clang or something like that, I only have to change it in one spot. Just like, miles per hour, or what was it? Kilometers per mile, or whatever it was. Right? You change it in one spot, and it's changed for everything. Then you have these rules. I want to build the program called image driver. These are its dependencies. It depends on imageutils.o, that object file, colorutils.o, that other library, and then finally the image driver, the main program right here. Those are its dependencies. How does it get built? It gets built by invoking the compiler with these flags, with these include directives, and you need this file, and this file, and then you output the image driver. Right? And also it includes at the end for different systems. Right? Okay, well, it depends on all those things. How do those get built? We have rules for those, for that one and that one. You can imagine, and this is a small makefile, but you can imagine if I had hundreds or thousands of different source files with different rules, and the rules change if I'm trying to compile it for SUSE Linux versus Windows, or Windows and Mac, or something like that. I put all of those rules into my makefile, and I don't have to worry about that problem ever again. All I have to do at the command line is type make, and I'm done. Right? What would it look like for our project here? I'm going to go ahead and steal this code. Let's come over here. Now let's create our own makefile. Again, you don't have to create your own makefiles. Anytime that that it's complex enough, we give you one. Right? But if you want to, you can. In fact, it's one of the advanced activities in one of the labs to read a tutorial about it and do it yourself. Right? But otherwise, I'm going to steal this. Those are all standard here. And I'm not going to build the image driver. I'm going to call my program loan program instead of a.out. Right? And it doesn't depend on these things. What does it depend on? It depends on finance.o and loan.c. How did I build it down here? Right? If I look at the old rules here, I had to build it. Where is it? Maybe I went past it. There. I built it like that. So it should look like something like this. Right? Loan.c, and then finance.o, and then I'm going to output the loan program here. The -o command is output. Instead of producing the default a.out, produce this file name instead. Okay. Am I done? I have a dependency on this object file here. How does that get built? Finance.o gets built. It depends on finance.c and finance.h. So that anytime you end up, okay, good, that is another quirk of make is that these have to be tabs. You can't space over. It's part of the language. You have to tab over. Don't ask me why. Right? I have to tab over my compiler, whatever that happens to be, my flags, my includes. And how did I build the finance library? Finance.o, output finance.o, GCC C finance.c. That's good enough. By default, it'll produce finance.o, right? With includes. There we go. Now, it was not that bad, right? It was only like two compile commands, right? But now I've gotten that down to one compile command. Just make it for me. Make. That's it. It's done. And it produced the loan program right here. Loan program. $10,000 at 5% interest over 5 years. Exact same program as before. Now, if I make a change, right? For example, the way that round descents somehow has magically changed. Instead of 100, we do need to go ahead and divide by 100.0. I change that file. Do I have to then specify, okay, I changed that one file, so compile that file, and this file depends on that file, and that file depends on that file? Nope, just make it again. Repeatable builds. This is a build system. Every language is going to have something like this. Java has Ant or Maven. Anybody? Python? Python's not really built. Python is a interpreted programming language, but I don't know. There might be something like this in it. They do have package managers. Pip. Anybody done Python before? I don't know what pip stands. Python package manager, isn't it? I don't know what the I, where the I comes from, but whatever. Anyway, making one change means that I only have to type one command. Make it. Make, right? And you can have multiple rules. For example, that's how you built the image driver program. I have a separate testing suite that I want built. Right? That can live right alongside it just fine. I have another rule here to clean up all my files. Remove all the temporary files that have a tilde after them. Remove all the object files and just clean up for me, please. Right? What was that? What would that look like? Let's go back over to our make file. There we go. And that is a tab. Good. So to invoke that rule, I would go make clean. See all these object files over here? They're going to go away because it automatically deleted them all. Right. Cool. Again, this is not a build class. This is not a, here's how you use make, right? I'm just showing this to you if you want to get into it. And you should know about it because this is an entire discipline unto itself. The last place I worked actually had 2 full-time employees doing nothing but build system stuff. I don't think that they worked with make. They worked with Ant and whatever C# uses. But they didn't write programs. They wrote programs to compile other programs. 2 full-time employees. And nowadays we call these folks DevOps, right? Development operations. They're not developers. They're not. They support. They are a support structure for the developers, right? They have to be developers because, of course, they develop scripts like this, and they do program stuff. But they're called DevOps, and it's an entire job, right? If you're on a small enough team where you can't afford to have a dedicated DevOps person, you probably have to end up doing this yourself somehow. But if you are in a large enough organization, you'll have either an individual or an entire team of individuals doing nothing but stuff like this. Right? That's how massive, complex systems can be. Right? Then you'll have an entire team for testing, an entire team for quality assurance, an entire team for human testing, et cetera, et cetera. Right? So any questions on that? All right. So for C, the make utility or the modern CMake utility are standard. Right? Read more about it on your own. I think that there's a suggested tutorial or something like that. But in the last 10 minutes here, what I want to do is I want to show you a demonstration, and we'll continue this next week, of how do functions actually work. You have this thing called a program stack. For that program stack, I'm going to go ahead and show you a visualization of a very simple program here. Where do I want it? Where is it? Some. There we go. All right. Here's my program. While we're waiting for it to compile here, let's walk through it and understand what it does. We've got 2 variables here in main, n and m, set to 10 and 16. We then call this function called average. By the way, never write code like this, right? If you want to compute the average of 2 numbers, you add them together and divide by 2 in one line. These should not be functions. I'm only creating these functions for demonstration of how functions work. So I wanted to keep it simple. We call this average function, and average function calls the sum function. The sum function adds them together and returns their sum. The average takes whatever the result of the sum was, divides by 2, returns that result. Let's walk through this. Yeah, there we go. Now it's better on the live stream. All right, so let me go ahead and create variables n and m. And before I call this average function here, observe where the variables are stored. N and M, they're in this blue box. That blue box is what's called a stack frame, okay? Every function call will have its own stack frame. When I call average, a new stack frame is created for the average function, right? A new blue box. And it has access to its own variables, A, B, and Y. A being the first parameter, B being the second parameter, and Y being a local variable right here. Right? Next, we call the sum function, which what happens? Another stack frame is created with A, B, X, and Y. It receives the value 10 and 16 as well. Now tell me, are those two A and B, this pair, A and B right here on line 1, and A and B on line 6, are they the same variables? No. They have their own box. Right? They have their own stack frame. This A right here with a value of 10 is not the same thing as this A right here with value 10. They have the same name. They have the same value right now, but they are not the same variable. If I were to change one of these variables, if I were to change this to 5, right, would that affect this one right here? No. They live in different stack frames. They live in different homes. They have different names. Right? Just because I say, hey, John, what's up? I don't know how many Johns we have here, right? But there are multiple Johns in here, right? Maybe. I don't know. But who am I referring to, right? They're all John, right? They're all A, right? They're all B, right? How do we know which one we're talking to? They have to live in their own box, right? John in the sum box, or A in the sum box, or A in the average box, and I have to refer to it that way. This is how functions work and how you can have the same variable with the same name in different scopes. Remember scoping, right? Where the variable is visible. This ends up how, this is how functions actually work. Every time you call a function, a new stack frame is created. Now, on this visualization, it's growing down, but don't think of it like that. Think of it more like a stack of dishes, right? You've got a stack of dishes, and it's always growing. Where do you put the new clean dish? Do you shove it at the bottom or in the middle somewhere? No, you're going to knock it over and crash it. Where do you put the new clean dish? On the top. We call that pushing because the dish analogy is from cafeterias. Right? We don't stack dishes up to the ceiling. We have this box here with a spring mechanism, and what do you do with the dish when you put it on the top? You push it down. That's why we call it a push operation. You push something on top of the stack. Now, when you take a dish off, do you take a dish from the middle? No, you take it from the same place, the top. And that's called popping because there's this mechanism there that holds the dish down, right? So that the spring doesn't spring all the way up, right? So you take one off and you pop it off the top. It makes a popping sound, maybe. Right? This stuff goes back to the 1940s. So their dish mechanisms made more noise back then, made a popping noise back then or something, right? So what's going to happen here when I return from this function? This stack frame here is going to end up being popped off the top and destroyed. What happened to those variables? They died. Right? They went out of scope. They were destroyed. That stack frame was destroyed. It was popped off the top. Somebody's using that plate. Right? We can't use that anymore. We can't look and see what was on that plate. They're gone. Any attempts to get them otherwise, nope. It's going to be undefined behavior, hopefully a segmentation fault. Right? This one returns. Its stack frame gets destroyed. Right? And when the program finally dies, then the entire stack gets destroyed. But this visualization doesn't show that. Okay? That has some implications. Let me go ahead and show you a very quick program here. Int A is equal to 10. Int B is equal to 20. And let me print them out. Print %D, %D. I'll print them in order, A and B. Oops, A comma B. And then what I'm going to do is I'm going to try to make a function called swap A and B. And I'll print them again. Right. So get rid of this. Void swap. Takes an integer A, it takes an integer B, and to swap two variables, we need to put one into the other and vice versa. So I need a temporary variable here to take on the value A. A can then take on the value B. and B will take on the temporary variable value. Right? To prove to you that this is not going to work, but maybe not in the way that it's completely apparent, I'm going to print them all over the place. Ignore that. Right. So let's walk through this program and understand what's going on here. A, B, 10 and 20. Right. When I print them out, what should it print? 10 and 20, and it does. I then call the swap function. Right. And I print them out. A and B they're 10 and 20 because I received them. I successfully swap them at line 6. Line 6 will print 20 and 10 because A and B have indeed been swapped. But which A and B? These guys right here. Have these variables been swapped? Nope. So, next. When I print those, what's going to happen? 10 and 20. It didn't swap them. It swapped copies of them. Right? And that's because of how functions work. Right? And in our last 2 minutes here, yes, I noticed some people smirking at the other thing. What's the obvious thing right there? The poop emoji? Right? Why? What's the poop emoji here in this case? It's their little joke, right? It's an uninitialized variable. What value does it have? Because I didn't give any command line arguments here. Null, it could be. It's garbage value, right? Uninitialized values have garbage values. You saw them before, they were question marks, but for this variable, it's just using that poop emoji, right? Hopefully that drives home the point. Uninitialized variables are garbage. Garbage plus 1 is garbage. It wasn't too common, but in your labs this week, if you got garbage values for the sums, it's probably because you started off with a garbage value. If you want to sum up a bunch of numbers and you go int sum, is that enough? What's stored in sum? Could be 0, but on CSE it was not in some cases. In which case it was garbage values, garbage plus 1, garbage plus 2, garbage plus 3 was still garbage. Always initialize your variables. And if it helps, remember that uninitialized variables are the poop emoji. Right? All right, next week.